Okay, so remember last time we proved that the Lebesgue integral is linear um, in general. So by in general, I mean if we have two bound and measurable functions, then you can pull out constants from the Lebesgue integral, and the integral of a sum is a sum of their integrals. And the Lebesgue integral is monotone in the usual sense. Okay. So let's put this to good use and see some consequences of this. So one important consequence is that the Lebesgue integral behaves like a measure itself. And I mean, of course, this is very important in probability theory. Because in probability theory, oftentimes you have a probability, a probability that's given by a probability distribution function. So a lot of times the probability that an event A occurs is going to be the integral of f of x dx over A for some positive function for some positive function, let's say f of x, and A is a subset of the real line, and the assumption is that the integral from minus infinity to infinity of f of x dx equals 1. Okay? So in general, we will prove that if f is non-negative, then integration against if f is measurable and doesn't really need to be bounded, but we'll get to the assumptions later. But so for a nice measurable function f that's non-negative, integration against f, we'll prove later, is going to behave like Lebesgue measure, essentially. It's going to behave like you would want it to behave. And this is kind of like a baby starting point for that fact, and that is if A and B are measurable subsets of some measurable set E with finite measure, and F is bound and measurable, then the integral of the disjoint union of A and B is going to be add up the two integrals. So here we're assuming A is disjoint from B. Okay, so how do you prove this? Well, first, it's very easy to prove, and I will have you do this for homework, that f times, well, particularly the characteristic function of A union B, if A union B are disjoint, is just a characteristic function of A plus the characteristic function of B. Okay, so multiply f by both sides, we get f characteristic function of A union B is f characteristic function of A, f characteristic function of B, added two up. So it's a little more work to do, and you can prove this either using the upper or the lower Lebesgue integral formulation of the Lebesgue integral, is that if I use the definition of the integral over E1 for any E1 as a subset of E that's measurable, that's the same thing as taking the integral over the larger set, but multiplying by a characteristic function. Okay? Very easy to prove, but again, I'll leave this for you to do for homework. Just playing around with, you can pick which one you want, either the upper or lower Lebesgue integral definition, doesn't matter. We're going to play around with whichever you pick, imps or soups, to prove this. Okay, right. So let's put these facts together. So A union B is measurable. It's a subset of E. A and B are measurable. So I can write this integral as the integral over E of f times its characteristic function. And I'm going to write this out at f characteristic function A, f characteristic function B. But I now know that integration is linear, and that's the whole point of this. So it's going to be, the integral of the sum is the sum of these integrals. And I'm going to use this one more time. So this is the integral over a of f of x, and this is the integral of b over f of x. Okay. So so right now for us, this is just a theoretical result that we'll put to good use in a minute. But we're going to have a lot more to say about this because, again, like this is super important in probability theory, that integration, particularly integrating non-negative measurable functions over subsets of the real line, just to be able to do that, and for this to behave like Lebesgue measure is extremely important. Okay, so an important corollary, probably the most important corollary of what we just proved, is the following. If A is a subset of E and EA is measurable, then I can write E as the integral of E, integral of f of x over the set E, as the integral of f of x over A, integral E take away A, integral of f of x over E take away A. So I can add these two up to get this integral here. Okay. So again, this is just like saying integration is behaving like Lebesgue measure. And what's the proof? All you do is write E as A disjoint union E take away A, and apply this result to to A disjoint union E take away A. So not exactly very deep, but it's very important, as we'll see in a minute. So another corollary well, this is a corollary to monotonicity of the Lebesgue integral. And when we end this section, we'll prove this and other things for complex valued functions, because in practice, particularly, both in probability theory and engineering and science, you want particularly what's called the Fourier transform. We want Fourier series. You want to prove facts about Fourier series. That's, the motivation for a huge chunk of this course. Probability theory and Fourier series, but also there's something called the Fourier transform that requires you to integrate complex value functions. So we'll get to integrating complex value functions later on. This will also be true in that setting, as is basically everything we do. But so this here is saying the absolute value of an integral is less than or equal to the integral of the absolute value. So the proof is very simple. Absolute value of f is measurable and it's bounded. If f is measurable and bounded. Okay, and we know that any real number is between minus its absolute value and its absolute value. So let's integrate this whole inequality here. So the integral of f of x is between the minus the integral of absolute value of f of x and the integral of the absolute value of f of x. Okay. And that implies exactly what we want, because hopefully you remember from basic analysis that for any two real numbers, a and b, well, b, sorry, it's not any real number, b is bigger or equal to 0, absolute value of a, whether it's positive or negative or 0, is less than or equal to b is the same thing as saying a is sandwiched between minus b and b. So here we're setting a to be the integral of f of x over the set E, and b is the integral of absolute value of f of x dx, which is going to be non-negative, because absolute value of f of x is non-negative. Okay. So yeah, if b is this integral here, a is this integral here, then we have this is true, and that implies this is true. It's equivalent. And this here with a being the integral of f of x, b being the integral of absolute value of f of x, this here is exactly what I want. So easy proof. Okay, so let's start talking about limits and integrals. Okay. So let's prove something very easy and not very interesting, because if we have Riemann integrable functions that converge uniformly to a function on everything's on a to b, closed interval a to b, then we should remember that the limit is Riemann integrable, and you can interchange limits and integrals. Okay, so uniform integral, the Riemann integral handles uniform convergence very nicely. Okay, and so does the Lebesgue integral, but the proof is going to motivate a much deeper proof, a much deeper theorem that we'll get to in a second. So if f of n are bounded and measurable on E is measurable, finite measure, and if Fn converges to F uniformly, then F is Lebesgue integrable, and we can interchange the limit and the integral. Okay. And what's the proof? And again, proof is very easy. So by assumption, F is bounded and measurable. You can prove, and I'll probably give this to you for homework. You should have proved this in basic analysis, but that's all right. That if Fn is a sequence of bounded functions, not uniformly bounded necessarily, but they're just assumed that we have bounded functions. We might have different bounds for each of these functions. And if Fn converges to F uniformly, then in fact, Fn has to be uniformly bounded, and F is bounded also. So F is bounded. It's in particular the pointwise limit of measurable functions. So it's measurable. So it's integrable. It's Lebesgue integrable. So without loss of generality, assume the measure of E is not 0. If the measure of E is 0, then I'm going to leave it as a homework to check that everything is 0. Okay? So it's not very interesting. Okay, so let epsilon be positive. Use uniform convergence on on E. So pick a big N where this is true on E, as long as little n is bigger than big N. Okay. So we're basically just going to integrate both sides, essentially. All right, so I need to prove that if little n is bigger than big N, then this is less than epsilon. If I can do that, then by the definitions of convergence of just, real numbers, this is a sequence of real numbers, this is a real number. If I can prove that this is less than epsilon, if little n is bigger than n, then this sequence of real numbers will converge to this real number. Okay, so use linearity, bring in the absolute value. Well, this absolute value here is less than or equal to epsilon over the measure of E. On E, because we're assuming little n is bigger than big N. And that's going to be epsilon. And that proves it. That proves that the limit of these real numbers is equal to this integral here. Okay, and remember, why do we say this is? Why do we say we can interchange limits and integrals? Well, the integral of a limit. The integral of the limit is the integral of f, because f is the limit of the fn's. So here we're kind of we're saying, well, I can pull the limit out. So the integral of the limit is the limit of the integral. Okay. So this is not very useful. I mean, it's sometimes useful, but it's very restrictive. So we're going to slowly remove restrictions on this result. The first result we have, which is quite useful actually by itself. So let's say I have a sequence of measurable functions that is uniformly bounded. So absolute value of fn of x is less than some m for some positive m for all natural numbers n. It's a little tough to read, but and all x in e. Okay? So if that's the case, and fn converges to f pointwise on e, then we have the same conclusion. We can interchange limits and integrals. Okay? So as I mentioned, this hypothesis is true, that if we have uniform convergence, then in fact the sequence is uniformly bounded. So this is much more general than what we just proved. And in general, when you have a result that has its own name, you know, it's usually pretty important. So ultimately, we're going to prove what's sort of like the gold standard, the theorem in like all of these when can you interchange limits and integrals, which is called the Lebesgue dominated convergence theorem. This is a special case of that, and we need this to prove that, and we'll prove that next week. Okay, so the way we prove this actually, it's a beautiful proof. It's pretty easy, and the way we prove that is we use Egorof's theorem. So remember, intuitively, Egorof's theorem says that pointwise convergence is, you know, the same thing as like almost uniform convergence. So if you're pointwise convergent, then you're almost uniform convergent in the sense that you have uniform convergence on a subset where E take away that subset has very small measures. So relative to E, the set of uniform convergence, set where you have uniform convergence is very large. It takes up a large portion of E. Okay, so let's actually write that down as a proof and see how that gives us what we want. So it's very easy to check that because we have a sequence of uniformly bounded functions and fn converges pointwise to f, that we have the same bound for f, well, except with less than or equal to. Okay. It's very easy to prove. Maybe I'll put that for homework. I mean, it's very easy basic analysis, but anyway. Okay, so again, f is a pointwise limit of measurable functions, so it's measurable. And this proves that it's bounded, so it's Lebesgue integrable. Again, we're going to assume the measure of E is finite, is not zero. If it's zero, everything is zero. So not very interesting. So pick epsilon bigger than 0 and pick some A that's measurable, that's a subset of E. So remember, Egorof's theorem actually says we can pick A to be closed. We don't care if it's closed, open, F sigma, G delta, you know, the union of G delta sets, whatever. We don't care. As long as it's measurable, we're happy. So pick A, subset of E, where A, again, takes up a large portion of E. So the measure of E take away A is less than epsilon over 4m. And remember, we're assuming E has finite measure. So we can use Egorof's theorem. And Fn converges F uniformly on A. Okay. So let's put uniform convergence to good use. Pick big N where this is true. for all x in A and little n bigger than big N. Again, we have uniform convergence on A, so by definition, just such a big N exists. Okay. So again, we're done if we can get that this is less than epsilon, because that'll prove that this sequence of real numbers converges to this real number. And we're going to do almost the same thing. We're going to exactly do the same thing on A. And we're going to use this fact on E takeaway A. Okay. So again, use linearity, smash in absolute values, and write this as the integral over A plus the integral over E takeaway A. So remember I said this is important to be able to do this, and here's why it's important. Okay, so we know that on A, as long as n is bigger than big N, we're assuming little n is bigger than big N, then this here is less than or equal to epsilon over 2 the measure of E. So monotonicity of the Lebesgue integral, this is less than or equal to integral of A, epsilon over 2 measure of E. Okay. Well, we don't have that nice of a bound for Fn and F, but we know both are bounded by big M. So by triangle inequality, this absolute value here inside this integral E takeaway A is less than or equal to, the integrand is less than or equal to 2 big M. Okay. Well, integrate this. Again, a constant is a simple function, so literally it's just going to be epsilon over 2 measure of E times the measure of A. Same thing here, it's this 2 big M times the measure of E takeaway A. Well, measure of A is less than or equal to the measure of E. A is a subset of E. So this is less than or equal to epsilon over 2. This is less than, remember, less than or equal to, less than epsilon over 4m. So the 2m's and the 4m's cancel, and we get epsilon. So that proves that we can interchange limits and integrals if we are dealing with a uniformly bounded sequence. So I'm not going to do examples. Maybe I'll do 1 or 2 examples, but I'm not going to dwell on examples because we'll do a lot of examples when we use this result to prove the much more powerful Lebesgue dominated convergence theorem. So this is really just a stepping stone to prove that much deeper Lebesgue dominated convergence theorem. It's a very special case of that. If you're curious what it says, you should do that. You should check that out. All right, so what we're going to do next time is we're going to start, what are we going to start? That's a good question. We're going to start section 4.3, and we're going to take the Lebesgue integral of a measurable non-negative function, but over a general measurable set, not necessarily finite measure. And we're not going to assume our non-negative function is bounded. Okay. So yeah, that'll be the next video, which should be up, I don't know, maybe a day or 2. So, all right, until then, so long, stay safe, and keep calm, carry on, and keep doing math.